Imagine a musician learning to play a violin. They do not just add more strings to the instrument to get better sound. They adjust the tension of the strings and the sensitivity of their bow hand. This is the core difference between standard learning methods and the approach we are discussing today. We are talking about how machines learn when the environment is not perfect. Specifically, we are looking at how intrinsic stabilization of synaptic plasticity can improve learning and robustness in artificial neural networks. This is a deep dive into the technical implementation, comparing intrinsic plasticity against standard Hebbian learning for edge devices with noisy sensor data. To understand why this matters, we first need to look at how traditional neural networks learn. The most common rule is known as Hebbian learning. It is often summarized by the phrase, neurons that fire together, wire together. When two connected neurons activate at the same time, the strength of the connection between them increases. This is a powerful biological inspiration. It allows the network to associate patterns in the data. However, when you apply this to complex systems, especially those running on edge devices, a significant problem emerges. Here is the thing. If every time a neuron fires, it strengthens the connections to its neighbors, the network can spiral out of control. This is known as runaway excitation. The activity levels in the network grow without bound. In a stable biological brain, there are mechanisms to prevent this. But in many artificial systems, the weights just keep getting stronger until the network becomes saturated. It loses the ability to distinguish between important signals and noise. This is particularly dangerous for edge devices. These are the small computers sitting in cameras, sensors, and IoT devices. They often deal with noisy input data. If the learning rule is too sensitive, the device might interpret a sensor glitch as a critical signal. It will update its weights based on that error, and over time, the entire system degrades. This leads to catastrophic forgetting, where the machine loses knowledge of previously learned tasks because the new noisy data overwrites the old stable patterns. Now consider this alternative. Instead of just changing the strength of the connections, what if the neuron itself adjusted its own internal state? This is the concept of intrinsic plasticity. In this framework, the system learns to adjust the internal parameters of the neurons alongside the synaptic weights. Think of it like tuning the sensitivity of a microphone. A standard learning algorithm might just turn up the volume of the amplifier, but intrinsic plasticity adjusts the microphone's gain control to ensure it captures the signal clearly without picking up background static. By optimizing intrinsic neuronal parameters, the network can maintain a stable level of activity even when the input data is chaotic. This dynamic adaptation allows the system to remain robust. Research into spiking neural networks is increasingly converging on the necessity of these dynamic, biologically inspired mechanisms. Static synaptic weights are simply insufficient for complex environments. Systems must adapt through evolving rules or parameters. There are frameworks like the plasticity-driven learning framework and spike-synchrony-dependent plasticity that explicitly address stability. They do this by learning the plasticity rules themselves or leveraging group synchrony to drive networks toward equilibrium. This directly improves multitasking and robustness. When a network can adjust its own plasticity thresholds, it can handle non-stationary environments much better. This means it can learn continuously without forgetting what it learned yesterday. Implementing complexity-based encoding and internal parameter adaptation allows artificial networks to dynamically adjust their plasticity thresholds. This leads to superior performance in continuous control and non-stationary environments. For example, imagine a robot navigating a warehouse with moving obstacles. The sensor data is constantly changing. A standard Hebbian network might get confused by the new obstacles and rewrite its navigation map. A network with intrinsic stabilization would recognize the change in input statistics and adjust its sensitivity. It would know to trust the new data without discarding the map of the warehouse layout. This is the difference between a system that breaks under pressure and one that adapts. The integration of neuromorphic hardware principles with intrinsic stabilization algorithms suggests a future where AI systems can learn continuously and robustly in real-world settings with minimal energy consumption. Biologically inspired learning frameworks that infer neural activity prior to synaptic updates offer a viable path to training deep networks without relying on traditional backpropagation. This improves energy efficiency and hardware compatibility. Standard backpropagation is computationally expensive and requires storing vast amounts of intermediate data. Intrinsic methods often rely on local rules that can be computed on the hardware itself. This is crucial for edge devices, where power and processing power are limited. However, a notable gap exists regarding the precise definition of intrinsic stabilization of synaptic plasticity as a unified mechanism. While some studies focus on parameter optimization or three-factor learning, which incorporates modulatory signals like dopamine, they do not always explicitly link these to intrinsic stabilization. Consequently, while all sources agree that moving beyond pairwise static interactions improves adaptability, the field lacks a standardized theoretical framework. Future work must bridge these distinct approaches to establish a cohesive understanding of how internal stability mechanisms facilitate superior learning. Despite this, the practical benefits are already clear. Systems that incorporate homeostatic plasticity prevent catastrophic forgetting and maintain network stability during continual learning tasks, mirroring biological resilience. Moving beyond pairwise Hebbian rules to incorporate group-level spike synchrony and dendritic compartment, specific plasticity rules significantly enhances learning efficiency and robustness in spiking neural networks. This is not just a theoretical improvement. It is a practical necessity for deploying AI in the physical world. The integration of neuromorphic hardware principles with intrinsic stabilization algorithms suggests a future where AI systems can learn continuously and robustly in real-world settings with minimal energy consumption. We are moving toward a point where machines can handle the noise of reality without needing constant human intervention to reset their learning parameters. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.